For a century, science has been telling us a story about what lies at the heart of a black hole. It describes a place called singularity, a single point of infinite density where gravity becomes so powerful it rips the very fabric of reality apart. It's supposed to be the final stop, end of the universe for anything that falls in. But what if that story, one at the center of our understanding of the black hole, is wrong? It's not a lie told with malicious intent. Think of it more like a blank spot on an ancient map marked with "Here be dragons." That spot, the singularity, comes directly from Einstein's revolutionary equations. Yet, most physicists today don't believe it's real physical object. They see it for what it truly is, a warning sign, an indication that our most trusted theory of gravity is incomplete. Because where the old story saw an ending, a new one is beginning to unfold. A story that suggests the center of a black hole isn't a point of total annihilation at all. It might just be the birthplace of something entirely new. To grasp why singularity might be a placeholder, you have to understand why we believed in it for so long. And that story begins, of course, with Einstein. In 1915, he completely rewrote our understanding of the gravity. It wasn't a force pulling things together, he proposed. It was a curvature, a warping of fabric of reality itself, space-time. Imagine a bowling ball on a rubber sheet. That's a star. A marble rolling nearby doesn't get pulled by the bowling ball. It simply follows the curve that the bowling ball creates. That's the planet's orbit. This idea, general relativity, has been fantastically successful. It predicts everything from GPS in your phone to the bending of starlight around the sun. But it also predicts an extreme scenario. Take a truly massive star. For millions of years, the outward pressure from nuclear fusion in its core holds back the inward crush of its own immense gravity. But eventually, the fuel runs out. The outward pressure from the fusion ceases, and an instant, gravity dominates. The star collapses in on itself with unimaginable force. While the outer layers blast away in supernova, the core just keeps falling inward and inward. The gravity gets so intense that it warps the space-time into a bottomless pit. At certain boundary, the warping becomes so extreme that the speed required to escape, the escape velocity, exceeds the speed of light. The equation for this boundary, the event horizon, is surprisingly simple. Rs equals to 2mg divided by c squared. It just means that the radius of the point of no return, Rs, depends only on the object's mass and a couple of universal constants. And cross it and you will never return because nothing travels faster than the light. You are now inside a black hole. So what happens to all that matter that fell in? According to Einstein's equations, it just keeps collapsing. Physicist Roger Penrose proved in 1960s that under the rules of general relativity, this collapse is inevitable. The math dictates that all of that mass, entire star's worth, is crushed into a region with zero volume. A single point. A point with zero volume but immense mass has a density that is mathematically infinite. Now you might remember the basic equation for density from school. P equals to m by v, or density equals mass divided by volume. If volume v becomes zero, then math says that density must approach infinity. The curvature of space-time becomes infinite. Gravity becomes infinite. This is the singularity. It's not just a place where physics gets strange. It's a place where physics, as we know it, completely and utterly breaks down. For decades, it was the accepted theory. It's what the math told us. The greatest theory of gravity ever devised predicted its own demise, right at the heart of the most extreme creation. This lie of the singularity wasn't just a story. It was a mathematical necessity of the theory, or so it seemed. In science, whenever you encounter an infinity, it's a giant flashing red light. An astrophysicist once recalled his high school physics teacher saying, "If you find an infinity, this is not physics, it's mathematics." Nature doesn't seem to do infinities. You will never find an infinitely tall tree or an infinitely massive planet. So, when an equation yields an infinite result, it often signals that the theory has reached the limit of its applicability. Now, this has happened before. Classical physics once predicted that electrons should spiral into the nucleus, radiating energy forever until atom collapsed in a fraction of a second. If it were true, the matter wouldn't exist. You and I wouldn't exist. But we do. Matter does exist. Infinity didn't mean atoms self destruct, it meant classical physics was being pushed beyond its limit. The singularity represents a point where general relativity breaks down, and the missing piece is believed to be the quantum mechanics. Physics in the 20th century was a tale of two theories. General relativity is the rule book for the very large, for stars, galaxies, and graceful dance of space time. It describes a universe that's smooth, continuous, and predictable. And quantum mechanics is the rule book for the very small, for atoms, electrons, and the bizarre world of particles. It describes a universe that's jittery, pixelated, and ruled by probability. In quantum realm, things don't have a definite location until you measure them. This means that energy isn't smooth, continuous flow, but comes in specific chunks. Nothing is certain. For the most part, these two theories operate in separate domains. You don't need quantum jitters to calculate the orbit of Mars, but at the center of the black hole, the principles of these two theories come into direct conflict. You have the mass of a giant star, an object of general relativity, crushed down to a size smaller than an atom, the domain of quantum mechanics. And here, the two theories provide completely different answers. General relativity insists on a smooth, continuous collapse to an infinitely dense point. However, the principles of quantum mechanics presents a fundamental objection. At its very foundation, the quantum world has a built-in fuzziness. The Heisenberg uncertainty principle, for instance, can be written as delta x multiplied by delta p should be greater than h divided by 4 pi. This equation clashes with the idea of a particle being confined to a single, infinitely small point. It says that more precisely you know particle's position, the less precisely you know about its momentum. Pinpointing a particle to perfect single point would imply an infinitely uncertain momentum, a physical impossibility. So, which perspective is right? Is the center of the black hole a smooth, infinite spike of space-time or a fuzzy, pixelated bundle of quantum phenomena? This conflict tells us that both the greatest theories are incomplete. To see what's really at the center of a black hole, we need a deeper theory, a theory of quantum gravity. And while we don't have a complete one yet, the clues it provides are pointing to something far stranger and far more compelling than a single point of nothingness. Welcome to the bleeding edge of theoretical physics. This is where the placeholder for singularity dissolves and a new reality begins to take shape. Physicists are developing several competing theories for quantum gravity, and while they differ on details, they are converging on one profound idea. The singularity probably doesn't exist. It's likely replaced by something else. Let's explore one of the leading proposals, which comes from a theory called loop quantum gravity. This theory reimagines the very basic of reality. In Einstein's view, space-time is smooth sheet, but in loop quantum gravity, it's more like a fabric woven by tiny, indivisible loops. Space-time itself is quantized. It's made of fundamental building blocks at an unbelievably tiny scale. This one change, making space-time pixelated instead of smooth, could change everything. Think of that star collapsing again. Gravity is crushing it smaller and smaller. But in this model, it cannot collapse forever because it cannot be squeezed into a space smaller than the fundamental pixel of space-time itself. As the matter approaches the ultimate density, the Planck density, some models predict a new phenomenon emerges. The quantum nature of space-time generates a powerful outward pressure. It's as if the universe fundamentally refuses to be broken down. The collapse halts and then rebounds. In this speculative picture, The star's core, instead of becoming an infinite singularity, forms an object of mind-boggling density but finite size. It's nicknamed a Planck star. It would be an object microscopically small, but still many orders magnitude larger than the theoretical Planck length. All of the mass of the original star is now in this ultra-compact quantum-ruled object. No infinity, no broken laws of physics. Now you might ask, if it bounces, why doesn't it just explode back out? This is where the effect of extreme time dilation becomes critical. The gravity is so immense that the time for Planck star slows down to a crawl relative to us. For the bouncing matter, it rebounds almost instantaneously. But for an observer on the outside, that bounce, stretched by gravity, could take billions of years. What we perceive as a stable black hole could, in this highly speculative view, be the longest, slowest explosion in history. Of course, this is just one of many ideas. A competing framework, string theory, has its own version of singularity-free black hole. Here, the entire region inside the event horizon might be tangled, messy ball of vibrating strings, a fuzzball. There is no singularity. Others, more exotic models, propose objects called gravastars, hypothetical spheres of dark energy. Even the renowned physicist Roy Kerr, who discovered the exact solution for rotating black holes in 1963, has argued that singularity is a mathematical artifact of an idealized model, not a physical certainty. The names may vary, Planck star, fuzzball, gravastar, but the central message of these research is same. The notion that a black hole must be an ending is being challenged. A new possibility revealed by quantum gravity suggests it's a place for transformation, where matter is converted into new, exotic state. The journey from the mathematical artifact to a new quantum frontier is what makes physics so exhilarating. It's a process of constantly pushing our theories to their breaking points and seeing what lies beyond. If you find this exploration of cosmic mysteries as fascinating as I do, consider subscribing and hitting that notification bell. We are always diving into the biggest questions in the universe, and your support makes it all possible. So let's say that singularity is just a placeholder. What if the center of a black hole is actually a quantum object? What does it mean? The implications are staggering, and they could ripple outward to solve some of the deepest paradoxes of physics. The most famous is the black hole information paradox. The core tenet of quantum mechanics is that information can never truly be destroyed. The unique information that makes you you can be scrambled or hidden, but it can never be erased from the universe. But a classical black hole seems to violate this rule. If you fall in, your information crosses the event horizon. Stephen Hawking showed that a black hole slowly evaporates by emitting what is called as Hawking radiation. But this radiation appears to be random. So when a black hole is gone, where did the information go? This paradox has been a major challenge for physicists for decades. These new singularity-free models offer a potential solution. In the fuzzball proposal, information isn't destroyed. It's woven into the stringy fuzzball itself. In the Planck star model, the information is stored in the star itself and then, after billions of years, could be released when the star finally completes its slow motion rebound. The paradox could be solved. Information wasn't lost, merely held in a state that is inaccessible for a vast period of time. This opens up an even more mind-bending possibility. The Big Bang theory, in its simplest form, suggests our universe began from a singularity, an infinitely hot, dense point. And just like with black holes, physicists are deeply uncomfortable with that idea. A theory called loop quantum cosmology suggests the Big Bang wasn't a beginning from nothing, but a big bounce. Our universe could be the result of previous collapsing universes that reached the maximum density, rebound, and reinflated. The singularity at the beginning of time could disappear, replaced by a bridge to a former cosmos. Could a black hole be the seed of a new universe? It's one of the most speculative yet exhilarating ideas in modern cosmologies. Is it possible that when a star collapses here, it creates a big bounce inside the event horizon, birthing a new universe in separate cosmos? In this scenario, black holes aren't just cosmic vacuum cleaners, they are cosmic parents, creating baby universes that are forever inaccessible to us. This is, of course, highly speculative. We have no direct evidence, but it's a natural extension of where the physics seems to be pointing. We began with this journey, what I called as lie, the singularity, a point of infinite destruction. It was a story born from our best theory of gravity, one that has defined our image of black hole for 100 years. But we have journeyed past the edge of that theory to a frontier where the rules of quantum world take over. And there we find a new truth emerging. The heart of a black hole isn't necessarily the end. It might be a place of ultimate transformation, a Planck star, a fuzzball, a new state of matter governed by laws we are just beginning to decipher. The singularity was a placeholder, a mathematical symbol for our own ignorance, but by confronting it, by refusing to accept an infinity as a final answer, physics has opened a door. Behind that door is not an abyss, but a new landscape of possibilities. Potential solution to information paradox, a possible origin for our own universe in big bounds, and a tantalizing idea that black holes might be the seeds of new universes. We can't see inside a black hole to prove any of this, but what we have learned is that its center may not be a breakdown of physics. It's a signpost pointing towards a deeper physics. It's not a full stop, it's a beginning of a next chapter. It's a profound reminder that in our universe, even most terrifying objects may not be about destruction, but about the endless, creative, and shocking power of rebirth. Thanks for watching.